Hello everyone, welcome back. In the last class, we were discussing about electronic configurations of atoms, and we have seen two rules that we need to keep in mind while writing these electronic configurations. The third rule is the Hund's rule of maximum multiplicity. Now, according to this rule, electron pairing does not take place in orbitals of the same subshell unless all of them are singly filled. Let us try to understand it by taking these p orbitals. We have px orbitals, py orbitals, and pz orbitals in the p subshell. Now, if there are 3 electrons, then electrons will be put singly like this first. Only then, after they are singly filled, we can put more electrons like this to pair them up. This pairing of electrons will not take place until all the orbitals have one orbital each, like this. So, if there are 3 electrons, it will be wrong to write the configuration like this. We cannot put 2 electrons here and this get empty. Likewise, in the p subshell, we have 5. In the d subshell, we have 5 orbitals. When we fill up electrons here also, we have to fill them up singly first, like this. Only after that, pairing of electrons will take place. So, according to Hund's rule again, electron pairing in orbitals of the same subshell will not take place unless all of them are singly filled first. Now, let us look back at the 2 other rules again. The first one was Aufbau's principle. According to Aufbau's principle, orbitals having lower energy are filled first. Only then higher energy orbitals are filled gradually. Then, according to Pauli's exclusion principle, an orbital can have a maximum of 2 electrons only. Then, according to Hund's rule, while filling them up, even though we can put 2 electrons in each orbital, pairing will not take place until all of them are filled singly first. Only after that, if there are extra electrons, pairing will take place. Now, giving these 3 rules in mind, we will go to writing the electronic configurations. But before that, again, let us try to understand again this again. Half filled and fully filled. The half filled and fully filled orbitals are more stable than the other kind of configurations. That means if we have the p orbitals, suppose the 2 p orbitals are 3, px, py, and pz. Each of them can accommodate 2 electrons. So, in the 2p subshell or in the 2p orbitals, we can put a total of 6 electrons. So, this p orbitals, if there are 6 electrons, they will be fully filled. If we have 3 electrons, then they will be half filled. So, 2p1, 2p2, 2p3, 2p4, 2p5, and 2p6. This one is half filled, this is fully filled. The half filled and fully filled p orbitals will be more stable than these other orbitals. Now, the reason for this is that the half filled and fully filled orbitals, they are more symmetrical. Symmetry leads to stability. So, if the half filled and fully filled orbitals are more symmetrical, then they should be more stable. That is one reason. The other reason is that in half filled and fully filled orbitals, there is more exchange energy. Electron exchange between orbitals can take place like this. The electrons can be exchanged between orbitals when they are half filled like this. And this exchange of electrons leads to release of energy. And since energy is released, these orbitals become more and more stable due to exchange of electrons. The exchange of energy, electrons, or the exchange energy is more in half-filled and fully filled orbitals. And when this is more, they will be more stable. So the first reason is because they are more symmetrical, and the second reason is because these are they have more electron exchange energies. And for these two reasons, half-filled and fully filled orbitals are more stable than the other configurations. So keeping all this in mind, let us now try to write the electronic configurations of some atoms. Suppose hydrogen. Atomic number of hydrogen is 1. That means it has only one proton and only one electron. Now, as we have done in the previous class, the orbitals can be arranged like this. 1s having the lowest energy, next comes the 2s, then comes the 2p orbitals, after that comes 3s, then 3p, then comes the 3d orbitals. But the 4s orbitals have lower energy than the 3d orbitals. That is what we have seen. So after we have filled up to 3p, 4s will be filled. Only after that we can put electrons in the 3 orbitals, because these have higher energy than the 4s orbitals. So giving this in mind, let us now try to write the configurations, electronic configurations for atoms starting from hydrogen. For hydrogen, atomic number is 1, so it will have only one electron, and that electron can be easily put here, because each orbital can have 2 electrons each. So we can put the single electron here. Therefore, the configuration of hydrogen will be 1s, 1 only, because there is only one electron. If we go to helium, its atomic number is 2. So it has 2 protons, 2 electrons, and therefore the 2 electrons can be put in the first shell, that is in the 1s orbital of the first shell. Now when we go to lithium, atomic number is 3. So there will be 3 electrons. So we put the first 2 electrons in the 1s orbital, then the next goes to the second shell, the s orbital of the second shell. This will be the configuration of lithium. Then after lithium comes beryllium with atomic number 4. So 4 electrons, we can put 2 electrons here, and in the 2s orbitals also we can put 2 electrons. So keeping in mind that these orbitals have to be filled according to their increasing energies, we can easily fill up electrons like this. The only thing is we have to know the atomic number of the atoms. Now let us take a higher atom with higher atomic number. Let us say sodium. Sodium, its atomic number is 11. So in the first shell we put 2 electrons, in the second shell s orbital we put 2 electrons, then in the p orbitals, because p orbitals are 6 in total, 3, we can put a total of 6 electrons in the p orbitals. So we can put 6 electrons here. Now we have 2, 6, 7, 8, 9, 10. We have put 10 electrons, 1 remains. This will now go into the third shell, the s orbital of the third shell. This will be the configuration of sodium. Now, for the sake of simplicity, sometimes when we need to write very long electronic configurations, instead of writing the lengthy configurations, sometimes we use the configurations of the noble gases. So here 1s2, 2s2, 2p6, 6, 8, 10. 10 electrons means the configuration of neon with atomic number 10. So in place of writing this entire thing, we can just write neon under these square brackets and then simply show this valence shell 3s1 like this. Likewise, for the next other elements like magnesium, atomic number 12, we can just write the configuration of neon represented like this, then 3s2. This will have 10 electrons. Then the remaining 2 electrons goes into the s orbital of the third shell. This is how we can represent the electronic configurations in short also. Then let us go to another atom with atomic number more than 20. Suppose scandium. Scandium with atomic number 21. If we write the entire configuration, it will be 1s2. This will have 21 electrons. So 1s2, 2s2, 2p6, then 3s2, 3p6. Then before 3d, we fill up 4s like this. Now let us see how many electrons we have put. 2, 4, plus 6, 10, 12, plus 6, 18, plus 2, 20. We have put 20, we have one more electron. And that last electron will come to the 3d orbital here. Remember, 4s orbitals have to be filled before the 3d orbitals because these have higher energy. So starting from scandium with atomic number 21, as we go up, they will be filled like this. 4s will be filled first, then after that 3d will be filled. Now, take the case of chromium, whose atomic number is 24. We can write 1s2, 2s2, 2p6, 3s2, 3p6, then 4s2, then 3d4. 2, 4, 10, 12, 18, 20, and then the last 4 electrons come here. If we follow the 3 rules that we have discussed, the Pauli's explosion principle, Aufbau's principle, and the Hund's rule, then the configuration of chromium should be written like this. Now here, up to here, we have 2, 4, plus 6, 10, 12, 18. 18 electrons. This is the configuration of argon, whose atomic number is 18 and has 18 electrons. So instead of writing this thing, the entire thing, we can write AR under square brackets, then we can write 3d4 and then 4s2. Now this should be the configuration of chromium if we follow the 3 rules. But as we have seen just a few moments back, half-filled and fully filled orbitals are more stable. So these d orbitals also will be more stable when they are half-filled or fully filled. Therefore, the actual configuration of chromium is written as 3d5 and 4s1 instead of this. Likewise, for copper, whose atomic number is 29, if we write the electronic configuration, we should be writing AR 3d9 4s2. 29, so 18 here, then 20, and the last 9 electrons will come into the 3d orbitals. But once again, the d orbitals will be more stable when they are fully filled in this case. So the actual configuration is 3d10 4s1. So in the case of chromium and copper, we are not following the 3 rules that we have, of course, not all of them, but we are deviating from the rules here. And the reason why we deviate from the rules here is because the d orbitals are more stable when they are half-filled or fully filled. And that is why the configurations of chromium and copper, they are said to be anomalous. You might be asked why chromium has the configuration 3d5 4s1 instead of 3d4 4s2. This is because d orbitals are more stable when they are half-filled. And in the case of copper, it will be because the d orbitals are more stable when they are fully filled. Now that is all we have from our chapter 2. Before I stop, I will just give a short introduction to chapter 9. That is about hydrogen. So far we have discussed Unit 1 and 2, and those are from physical chemistry. This chapter 9, which is about hydrogen, it is from inorganic chemistry. Now, hydrogen, it is the lightest element. It is the lightest element among all the elements that we find, and it is the element with the simplest atomic structure. It has only one proton, it has no neutrons, and only one electron. Therefore, the configuration of hydrogen is 1:1, and if we draw the atomic structure, we will have the nucleus with no neutrons and only one proton and only one shell with a single electron. This is the simple atomic structure of hydrogen. So not only is it the lightest element, it is the element with the simplest atomic structure. Now, hydrogen in its gaseous state, it exists as a diatomic molecule, H2, and therefore we call this as dihydrogen also. So for the sake of simplicity, we refer to it as hydrogen only, but it is also called as dihydrogen because in its molecule there are two hydrogen atoms. The study of this hydrogen is very important because it is one of the most sought after elements, and it is one of the sources of energy for the future, one of the important sources of energy for the future, and therefore the study of this hydrogen becomes very important. Hydrogen, it exists as a diatomic molecule, H2, in the gaseous state, and due to the presence of these two hydrogen atoms in its molecules, it is also called as dihydrogen. That is what I have just mentioned. Now, these two hydrogen atoms, they are joined by a covalent bond like this, and this bond has very high bond dissociation enthalpy, and due to its high bond dissociation enthalpy, hydrogen molecule is very less reactive at room temperature. But atomic hydrogen that is obtained by dissociating this hydrogen molecule into its atoms, the hydrogen atom will be very highly reactive. So if you are asked why hydrogen molecule or dihydrogen is less reactive at room temperatures, it is because of its high bond dissociation enthalpy. Now, the name hydrogen was given by a scientist, Lavoisier, as it produced water when burnt. It comes from two Greek words, hydro, meaning water, and genos, meaning producer. So hydrogen means water producer. Since hydrogen produced water on heating, it was called as hydrogen by this scientist Lavoisier. That's in the gaseous state, it exists as a diatomic species, H2, once again, and therefore it is also termed as dihydrogen. Hydrogen is the first element in the periodic table. However, its position in the table is debatable because it resembles both alkali metals as well as halogens. Moreover, although it resembles both alkali metals and halogens, it differs from both in certain respects. So the position of hydrogen in the periodic table is debatable. Let us see why this is so in the next class.